Hello students. So I'm going to discuss about group isomorphism. In our class, we have already discussed about homomorphism between two groups G and G bar. Here we will discuss about isomorphism between two groups. So this notion was first introduced by Galois, whom we also refer as Galois. About 180 years ago, the term isomorphism is derived from the Greek word isos, meaning same or equal, and morph, meaning form. So what is the definition of group isomorphism? So we already know homomorphism between two groups is a function from G to G bar which preserve the group operation. And isomorphism phi from a group G to a group G bar is nothing but a homomorphism where the function is 1, 1 and onto also. So in symbols, we write that this function phi from G to G bar is isomorphism when it satisfies or when it preserves the group operation like this way: phi AB equals to phi A, phi B for all elements A and B from G, and this function phi needs to be 1, 1 and onto also. And as we already know, the group operation between A and B is from the group G, and the group operation between phi and phi B is from the group G bar. If there is an isomorphism from G to G bar, then G and G bar are called isomorphic, and in symbols we write this notation: G equivalent to G bar. As already the term suggests, isomorphism is nothing but same form. It is about same form. So whenever there is a isomorphism between two groups G and G bar, so we will algebraically consider these two groups as equivalent or similar. Let us consider this diagram. So as you can see, there are two elements. We have considered two elements A and B from the first group, which is under the binary operation of G is combined to AB, and the image of these two elements under phi is phi A and phi B, which is combined as the elements phi A, phi B under the operation of G bar. So under phi, this image of this element AB from the first group will be related to this element phi A, phi B of the second group. So this is the visualization of isomorphism or graphical or diagram representation of an isomorphism. And suppose we have considered, so all the group operation in a group can be classified into product or plus, as we have already discussed in the classes. So what will be the form in that case? Suppose the group operation in G and G bar both are product, then what will be the form of the operation? Operation preserving form will be which one? So phi A dot B equals to phi A dot phi B. Suppose the group G is with dot and G bar is along with the operation plus, then what will be the form of the homomorphism? So phi A dot B will be phi A plus phi B. Similarly for plus and dot and plus and plus. So all these four cases are what will be the form of the element when we apply an isomorphism on the group operation. So let us see some examples. So few examples of group isomorphisms I have tried to given, but as you know, in book there are lots of examples. You can consider those examples also from your understanding point of view or from the examination point of view. I have just given the 3-4 examples just to clear the concept. So first example I have considered, suppose G be the group of real number under addition and G bar is the positive real numbers under multiplication. So then these two groups G and G bar both are of real number. One is all the real number, another is only the positive real number. So these two groups are isomorphic under the operation phi x equals to 2 to the power x. So there is a very good illustration or verification of this example in your books, so you can go through it. In this video presentation I have excluded that part of explanation. And infinite, another example. These two are very strong example of group theory. So any infinite cyclic group is isomorphic to Z. That means you take whatever cyclic group which is infinite. From that cyclic group you can always define a function to the group of integers under addition. Similarly, another example, this is not actually an example, this is an result also, but I have given as an example. So you take any finite cyclic group which is generated by A and of order n, suppose, then that finite cyclic group is always isomorphic to Zn. That is the group of integers under addition modulo n. So I will suggest you to go through the explanation of all these three examples. So next, let us consider one example in which we cannot define homomorphism between two groups. Okay, so there is, suppose, consider the group Q of all rational numbers under addition and the group of non-zero rational numbers under multiplication. So between these two groups, we cannot define any isomorphism. Okay, you remove isomorphism. Not only we cannot go the isomorphism, instead there is no homomorphism as such. So what will happen then? Suppose we have considered one isomorphism from Q to Q star. So if phi is a isomorphism from Q to Q star, then definitely phi is a 1-1 onto isomorphism from phi Q to Q star. So what will happen then? 1-1 onto homomorphism. So it is an onto function. So for every element in Q star, there will be an element in Q. So consider the element -1 in Q star. Since it is an onto function, there should be a rational number A in Q, so that phi of A should be -1. What will happen then? So what will happen then? So we get -1 is equals to phi of A. Now we can write this element A, this rational number A, as A by 2 plus A by 2. Since phi is a isomorphism, it is a homomorphism, so this addition will be converted into the group operation of the second group, which is multiplication. So phi A plus A by 2 plus A by 2 will be break into phi A by 2 plus into, product phi A by 2, and this will give phi A by 2 whole square. Now see, phi is a function from Q to Q star. So A by 2 is an element from Q. So phi of A by 2 will be an element of Q star, which are rational numbers. So what we have obtained? That product of a rational number is -1. Square of a rational number is -1. But we already know square of a rational number cannot be -1. So if we consider, if possible, if we assume that there is a isomorphism from Q to Q star, we will get this contradiction. Okay, so there cannot be an isomorphism between the addition group of rational number to the multiplication group of non-zero rational number. Okay, now there are lots of examples in your book, and there are some interesting properties of isomorphism which I will discuss in the next video. So before going to properties of isomorphism, let us discuss one very celebrated theorem of group theory, which is Cayley's theorem. So this theorem is named after great mathematician Cayley, and you have already heard about this name Cayley when we construct Cayley's table for group operation. Okay, so what is Cayley's theorem? It is given in 1854 that every group, irrespective of its operation, whether finite or infinite, is isomorphic to a group of permutations. That means given any group G, that group G will be isomorphic, or there will be an isomorphism from that group to a group of permutations. Okay, so what will be the proof? We will go step by step. First of all, consider G be any group. Okay, so our primary task is to construct a group G bar of permutations which is isomorphic to G. And remember what is a permutation? It is a 1-1 onto function from a set to itself. Okay, so what will be those permutation in this group G bar? That we have to construct by ourselves. Okay, because we have given only this group and no more information is given. Okay, so then what will be that function? So how to define a permutation? So for any element G in G, define a function Tg from G to G, from the group G to the group G by this formula, that Tg of x is Gx. Okay, for all element x in G. Now you see this small g is an element of the group G. This small x is an element of the group G. So this product, there is a between these two elements the group operation is there. So by closure this will again be an element of G. Okay. So by the definition it is a permutation. Okay, by definition it is a function from G to Z. We have to verify whether it is a permutation or not, that is 1 1 on 2 or not. So for 1 1 Tg is 1 1. Why? Because consider this one, Tg of small x equals to Tg of small y. So by the definition of function it will be gx gy, which will give us by cancellation of group that x equals to y. By the cancellation property of group it is x equals to y. Then Tg is on 2. Suppose you consider any element x in the codomain group. Okay. Then as we have already fixed this small x, small g element, then x belongs to the group. So G is an element of group. Definitely G inverse will be an element of the group. And if G inverse and x are element of group, then their product G inverse x is also an element of the group G. So that what we will get under this function Tg, what will be the image of G inverse x? So Tg of G inverse of x, G inverse x is by definition G inverse of x, which will give us by associativity x. Thus, for every element x in the codomain group G, there is an element G inverse x in the domain group G, so that Tg of that element, image of that element under Tg is x. So our function Tg, here I should write Tg, but by mistake I have written T. This function Tg is on 2. So thus Tg is a permutation on G. Now consider all such permutation on G. Okay, corresponding to every element G, small g in capital G, consider the collection of all such permutation. Okay, so our next task is to prove that this collection is a group. Since it contains all permutations, so this will be a group of permutations. Let us check whether this is a group or not. So before proving group, to prove group, we already know that we need to prove whether associativity, identity, inverse, and closure, these properties are satisfied in this set or not. First of all, consider this one. First of all, observe this one, that you take any two permutation from this collection Tg and Th. What will happen if we take composition of that two function Tg, Th of x? So by definition of composition, this is the case. Tg, Th, x is Tg of Thx, which will give us, see, this will give us Tgx of x. That means these two, product of these two permutation for these two different elements is nothing but permutation corresponding to product of the elements. So what we will get, Tg, Th equals to Tgh. Now, so what will be the identity element of this group? So as this group contains identity, consider the function Tg or permutation Tg corresponding to the identity element. So Te, as our notation is as our notation has asked. So Te. So what will happen when we apply or when we take composition of Te with any other element Tg from this collection? So Te, Tg, Te, by this product composition of function, it will give us Tge, which is Tg, and we can write is Te, Tg. So this function, this permutation Te corresponding to the identity element of G is the identity function or identity element of this set T bar, G bar. Now, for an element Tg in G bar, so consider any permutation Tg in G bar. Consider this permutation, as small g is an element of capital G, so it will contain its inverse also, and you consider that permutation corresponding to inverse of G. So what we will get them? Tg and Tg inverse product will give us the identity element of this group, which is T. So inverse of Tg will be Tg inverse. Okay, and definitely this will be an element of G bar. So what it suggests, corresponding to every element Tg in this collection, there is an element Tg inverse in this collection, so that it is inverse of the given permutation. And as we already know, composition of function is associative, so it is true for permutation of this group also. Okay, so all the condition, and this condition is for closeness. You take any two element in this group, in this set, their product, which is this element, is also in this set. Okay, so closure, associativity, identity, inverse, all four conditions are satisfied. Now, as all the condition for a group 2 is verified, so it is a permutation group. It is a group of permutation. Now, so we are given this group G and we have construct one group of permutation. Now define a function phi from the given group G to the permutation group G bar by this one. Phi of an element, image of an element G, small g from capital G under phi as Tg. Now this function is well defined and 1 1. So for 1 1 proof, see, you take phi g equals to phi h. So phi g equals to phi h will be Tg equals to Th. Two functions are equal when their image under for every element are equal. So Tgx equals to gy, Tgy. In particular, since this is true for all element x and y from G, so it is true for the identity element also, that is T G of E equals to T H of E, which will give us G equals to H. And reversing the process, we will get well defined. So under these steps, we can conclude that phi is well defined in 1 1. Now by the construction of function, construction in the permutation phi is onto. That means you take any element Tg in the permutation group G bar. So to form this element Tg, we definitely need this element G from the parent group G. Okay, so by definition it is onto. Now finally, what will be the homomorphism? How this function behave, whether this function can preserve the binary operation, group operation between the groups or not. So you take any two element A and B from the given group G. So phi of AB, which is, so by definition it will be TAB, and here we have already discussed what is T of product of two element. So T of product of two element is nothing but product of T of individual elements. Okay, and that is phi equals to phi AB. So phi is a 1 1 onto homomorphism from G to G bar. Therefore phi is an isomorphism, hence our given group G is isomorphic to this permutation group. Okay, so for this class I will conclude here. We have to discuss about different properties of isomorphism, and we need to consider some other examples also. Okay, so that part I will discuss in the next video. So for this presentation or for this class, I have considered your textbook, your referred textbook as per GU syllabus, which is Contemporary Abstract Algebra by Gallian. Thank you.